would like to thank the organizers very much for inviting me to this exciting symposium. I'm a computational neuroscientist, and we perform large-scale simulations of networks of point neurons to understand some of the phenomena ultimately that Rainer talked about. But actually I'm concerned with more basic questions at the moment, which revolve around how does the complex connectivity structure of the cerebral cortex of primates give rise to the neural dynamics. And since this symposium is about the three worlds model, I was asked to place our work in the context of this model. And maybe some obvious things. So if we perform simulations, then we have to assume that the relevant brain physics can be represented mathematically, of course. Although we are looking at dynamics in the first place and not really at brain function in the sense of information processing, ultimately we do assume that the corresponding biophysics captures mental processes, at least a lot of relevant mental processes. If there are non-algorithmic ways in which the brain works, then we would not capture that. But I might venture onto thin ice and say that I think that that may not be necessary in order to explain these mathematical insights, because I think that we never reach absolute 100% certainty with our minds about mathematical statements, and so non-algorithmic computations may not be necessary to account for our near certainty about them, I would say, but this is of course a contentious issue. And when we perform simulations, we have to make some further assumptions. So there's an intermediate step between the mathematical equations and the physics, which is the implementation. And we have to assume that we correctly implemented the mathematical equations, but this is always an approximation. Presumably it's a very good approximation as long as you have a very sort of high resolution representation of the numbers, if you have an appropriate integration scheme. But still we cannot put them exactly into the computer. And at some level, brain dynamics is very likely to be chaotic, and which also means that we can only compare the results of our simulations in a statistical sense with experimental results or with the results of simulations with other tools, because even very tiny differences in the representation of the numbers or in the integration scheme will lead to differences that blow up after a while. So we also have to assume that statistical properties of the brain dynamics are relevant for our simulation results to be meaningful. Now, what exactly are we trying to understand? On the one hand, we know that the cerebral cortex has a very complex organization and connectivity structure on multiple scales. And on the other hand, we know that the brain dynamics displays features on multiple scales, from the level of local populations of neurons. When you look at the spiking activity of them, there's a broadband activity, including multiple frequencies. And at a more global scale, there are so-called resting state networks, as observed with functional magnetic resonance imaging, that consist of groups of areas that co-activate on a time scale of seconds to tens of seconds even when the subject is not doing anything in particular. So that's what this resting state refers to. There's no task or so. And so we would like to understand how this complex connectivity gives rise to this multi-scale resting state dynamics in the first place. And this resting state dynamics has other features like differences in the mean firing activities of the different types of neurons in the different cortical layers. So this is here from an experiment on rat in different states. And you see that in layer 2, 3, the spiking activity tends to be quite low, and then in layer 5 it tends to be higher. And the propagation of activity across areas has also been investigated. Here, these are results from an EEG study in which subjects were either looking at a visual scene or they were performing mental imagery, so they were imagining those scenes. And the researchers found that in visual imagery, so in the latter condition compared to the perception, there was more flow of activity, so more influence from parietal regions so parietal to occipital regions. Which we would refer to as feedback from higher order to lower order visual areas. And our model of choice, our system of choice, is the vision-related areas of the macaque cortex, so the macaque monkey, both because of the availability of extensive experimental data and because we think it will be a good stepping stone to the human brain. And furthermore, it has a more or less regular organization that can be captured in these visual hierarchies, as depicted here, that are based on pairwise laminar connection patterns between the areas. So, so primary visual cortex as the first cortical processing stage for visual information is at the bottom of the hierarchy, and then the area that Reiner talked about is here, for instance, so representing higher level aspects of vision, all the way up to prefrontal cortex. And so, but how do we then go about modeling this? So if we want to capture the microscopic aspects of the activity, then it's clear that we need to have individual neurons in our models. But can we, for instance, take 100 neurons and connect them with 100 synapses per neuron or so? And it turns out that that the general answer is no. We found that this downscaling with respect to nature distorts the activity correlations between the neurons. So, and this seems to be important because the correlations are task-related, as here shown in an experiment on the hippocampal CA1 region of a rat performing an auditory visual discrimination task. And the task-related correlation was only seen in the visual task. Here the x-axis represents the time lag between the time series for the two neurons that are considered. And so if we want to model this type of thing correctly, then we would ideally have the full number of neurons and synapses. It was already known before that when you reduce the number of neurons, then that tends to increase the correlations between the neurons. You can think of this intuitively as if you have a fluctuation in some part of the system, that it would have a relatively larger effect on the rest of the system if you have a smaller system. So, but we also found that when you reduce the number of synapses per neuron, even if you try to make up for their smaller number by increasing their strength, it changes the shapes of the correlations. And this would distort things like spike timing dependent synaptic plasticity, apart from and quite apart from the fact that if you want to test the goodness of an approximation obtained by downscaling, you would have to compare at least with full-scale simulation. So ideally, we model the full number of neurons and synapses in the natural system. And in our case, we focus on one hemisphere of macaque cortex and all vision-related areas there. They contain about 800 million neurons in total, each sending and receiving on the order of 10,000 synapses. And for that, you need advanced simulation technology, which is provided to us by this neural simulation tool, NEST, which is developed for a large part in Jülich. And the largest simulations that have been performed with NEST have included about 2 billion neurons on a supercomputer. And so in principle, it's possible to perform these simulations. In the latest development of this simulation technology, the memory consumption of the compute nodes has been made independent of the network size, so that in principle the simulations could scale to the expected next generation supercomputers, which have a performance of on the order of 10 to the 18th floating point operations per second. But this would be extremely, it would cost a large amount of energy, and it's not good for, so the turnover rate is very low. So in practice, we consider just 1 square millimeter cortical circuit to represent each area. We have 32 areas that are vision related according to this particular parcellation that we use. And then we reach about 4 million neurons connected via 24 billion synapses. And we simulate it using NEST on a supercomputer in Jülich. As a building block for each area, we use this very simple model with an excitatory and an inhibitory population of point neurons in each layer. So excitatory neurons, they increase the firing probability of their target neurons, and inhibitory neurons decrease the firing probability of their target neurons. We have these layers, so 2, 3, 4, 5, and 6, and layer in cell type specific connection probabilities that are based on extensive experimental data. And all the neurons receive an external stochastic drive to represent the non-modeled parts of the brain. And what this then leads to is this so-called asynchronous irregular state that's observed in cortex in vivo, where if you look at each neuron, so represented here in this raster plot, the spikes of each neuron occur at irregular intervals, and the asynchrony is seen by the fact that you don't see clear vertical stripes in the activity here. And yeah, so we have these layer-specific activities that you saw before, with the lowest activity in layer 2, 3, and the highest in layer 5. That's based on the connectivity, because the intrinsic properties of the neurons in this model are taken to be the same. Then in our larger model, we also need to have the connectivity between the areas that we base on so-called axonal tracing, in which a dye is injected into a particular area, and then it gets taken up by the axons, and it's transported either in the forward direction, it's called anterograde tracing, or in the backward direction, called retrograde tracing, depending on the dye. And this is an illustration of retrograde tracing. So where the sending cell bodies are, the dye ends up in the sending cell bodies. And here you have the laminar patterns of the stained cell bodies going up the visual hierarchy and going down the visual hierarchy. Because these data are not complete, we need to use statistical regularities and dynamical constraints to fill in the gaps. And then we obtain a connectivity map at the level of the areas, layers, and neural populations. And then we turn on the simulation and see that there are these slow activity fluctuations that appear in the different areas that were not there in the isolated microcircuit. So these are due to the interactions between the areas. And in particular, we need the synapses between the areas to be intermediate in strength, so that the system always goes close to an instability between a low activity and a high activity state. And close to the instability, the dynamic slows down. And that's where these slow fluctuations appear. You saw in the beginning that the experimental data also showed these fluctuations on different time scales. So these are from the experimental data for 140 neurons recorded in parallel. They show periods of less or more synchrony. Overall, the spectrum looks like this yellow curve, and then from the simulation is the black curve. Fits more or less, except for that bump. And also the distribution of spike rates is similar to the experimental data from primary visual cortex. And also shown here is that when you take weak or strong cortical synapses, it's no longer the case. So it's specific to the state of just below the instability. We also looked at the activity propagation across the areas and find that it's mostly in the feedback direction. It goes from parietal to temporal to occipital regions, and then followed by trough in frontal regions. That's similar to during the visual imagery that I talked about in the beginning, also as during sleep, which it makes sense because our model is not processing any visual inputs really. We can also understand what determines the propagation direction. I will not go into it now. Finally, we looked at the so-called functional connectivity. That's a word that neuroscientists use for correlations in the activity between the areas. And when we compare with correlations or functional connectivity from fMRI, from monkeys, and see that the correspondence between the two is also best at the same value of the cortical synaptic strengths, where the microscopic spiking activity is the most realistic. So it suggests that we are really capturing something about cortex. So I will not go into the conclusions, but this model is far from perfect, but we consider it to be a good stepping stone for further developments. And here are some things we're already working on, is try to understand why the widths of the autocorrelations of the neural activity increase up the visual hierarchy. Some people think this is important for visual processing. Adding further cortical areas, comparing with further experimental data. We're also working on a model of human cortex. And ultimately, we want to understand how the brain really works, processing information, so we have started looking into that. And I have a lot of people to thank, and I thank you for your attention.
Great, thank you very much. Based on a discovery data set, I now have a hypothesis that my phone ignores it when I try to turn the sound off, so my apologies, Sacha and Rainer. Next time I give a talk, you should turn your ringers on. Mm-hmm. Okay, have we got any questions? Okay, I might actually start with one myself. Mm-hmm. So you mentioned the work of Markov, who has, a lot of this, these are tracer measurements where you're sort of, in a very invasive way mapping which brain regions are connected to which other ones. Mm-hmm. And I think for a long time we had these sort of ideas of a very small set of discrete connections that existed between a relatively small number of brain regions. And I think one of the things that was kind of shocking to a lot of people was when he showed that actually basically lurking under the surface were connections between, it seems like almost every pair of brain regions. Mm-hmm. And obviously you need to start with something simple, but I'm curious what you think about the need to include those in these kind of simulations. And what do you think about the idea that we have, sort of many orders of magnitude of strength of connections in terms of like number of neurons that are connected between multiple brain regions?
Yeah, so we include those connections that they have found. And but I think more important than this binary view is to take into account the connection densities, because they span many orders of magnitude. There's a little issue with those studies in that if you look at data from lots of different animals, all their brains are slightly different. So ultimately you can end up with a fully connected network if you don't do the statistics properly. So yeah, that's one issue, but it's another reason to not look at the binary graph.
More philosophically, I mean, what do you think about the fact that, because I think this is something that people are kind of struggling with, to wrap their heads around what it means to have so many orders of magnitude of differences and connections. Like what are these relatively sparse connections, for example, doing in the brain?
Yeah, I think that the sparsest ones are not doing much, but some of them may yield robustness to if you lose if some part of the brain is damaged, then other parts can take over if they have at least sort of a seed for the connectivity that they can expand on. That's my guess.
Okay. Have we got other questions from the audience?
In the field of artificial intelligence at the moment, the so-called deep neural networks are very popular. And I wonder whether you can give them some advice to make their networks more detailed, better, and whether you can tell something about the comparison between your very biological detailed models and the very sparse models in artificial intelligence, these deep neural networks.
Yeah, so we haven't really done that yet, but there are others who have done that, and the first step is to try to find an equivalence between the layers of the artificial neural network and the areas here, for instance, and see if then the average connectivities are similar. You can make them similar and see how does it affect the performance of the artificial neural network, and vice versa. If we let the artificial neural network learn, do we obtain a structure that's similar to what we see? And then there are other ways that look at more representational similarity. So you can let both subjects and artificial neural networks solve lots of different tasks, and then or look at lots of different objects, for instance, and then see how similar is the output or the experimental activity between these two objects, between all pairs of objects, and then see what model captures that the best. So those are some ways that you can go about.
Well, I look to see if we have any more questions. I do have at least one, if nobody else does. But it's sort of so. One of the things you mentioned quite a lot about feed-forward and feedback connections, and I think one really intriguing idea about what the brain is doing is that it's fundamentally not a taking in sensory information and processing it unit. It's a make a prediction and then look to see if that agrees with the input that you had, right? Which is sort of saying that these a lot of feedback connections are fundamentally about sort of testing error. Mm-hmm. Do you think? I mean, what do you think in terms of like how much evidence there is for that? Do you think that is a sort of a general principle, or do you think we just don't know at this point?
I personally quite believe in this predictive coding scheme, but it's a re-entrant loop system. So it's not either like visual perception or making predictions, but it's a continuous comparison of both at all the levels of the hierarchy. That's what I think.
Okay, that's great. Any last questions before we move on to the next speaker? Okay, wonderful. I also have a bottle for you. you very much.
Thank you.
Thank you very much.